And so now let's take a look at how to find the capacitance for a spherical conductor. All right, so spherical conductor, very similar to cylindrical in that, well, in this case, it doesn't have a length. It's basically, well, a ball or a point of charge. So the central, whoops, let's do, that has radius of A and total charge Q. And the outer spherical shell has radius B and total charge on it of minus Q. And again, these are both conductors, and so this configuration is a spherical capacitor. And they are completely charged up. So that means there's an electric field that goes from the inside out. Write that like that. And we want to find, again, the capacitance, which is written as C is Q over V. Okay? So we need to find the charge and then the voltage. So normally we use Gauss's law, right? In this case, though, like in the cylindrical case, the electric field is not constant, right? The electric field magnitude is different here than it is further out at a different distance. So thus we can't keep it constant and just use Q in our capacitance. We have to solve for an expression for the electric field. That's okay. We know how to do that. So we have epsilon naught times the closed integral of E. And so, well, we need to make a Gaussian surface, first of all. So our Gaussian surface is right there. Let's call that radius radius r. Okay, and the dA for that Gaussian surface points outwards. And so at that surface, right, the electric flux is constant at all points at that distance, so we can pull that E out of the integral. And now we have closed integral of, well, dA at that distance r. The angle in between E and dA is 0. They're both pointing directly radially outwards. So that's cosine 0, which is 1. And now epsilon naught times E times the area of that Gaussian surface. Well, this is 4 pi r squared. So the electric field is, well, what you may have suspected to be a point charge, Q over 4 pi epsilon naught times r squared. Okay. And now we need to find the voltage in between. So we can do that as V is the negative integral from our initial to final, and we are free to choose those, again, of E dot ds. So we are free to choose the direction of our ds vector, right, of our path length. Do we want to go from inside out or outside in? Well, again, that negative sign in front is kind of wonky, right? I don't really want it in our capacitance expression, so we have a way to get rid of that. Namely, like in the last case, we want to go from the outside in, the negative plate inwards. And so if that is our ds, I'm going to say ds is then negative dr, because going from the inside radially outwards is, well, the r hat direction, in other words. So we can even write that as, and there's so many arrows going on, I know, but that direction is in the r hat direction, right? So ds is in the minus r hat direction. So that takes care of the negative. It's still minus to, or sorry, initial to final, E dot dr now, and now we can evaluate. So initially, I'm saying we're starting from the outer conductor going towards the inner conductor. So that means integral of, what am I doing here? B to A times E dotted with dr. Okay, well, that's a little redundant. Let's start evaluating here. Integral B. Now let's just plug in the electric field that we found from earlier. There we go. Q over 4 pi epsilon naught r squared, and dr, that's our magnitude, and the angle in between E and dr, in this case, well, the electric field is outwards, and, well, it's not dr necessarily, remember, it's still quote-unquote ds. We just put it in terms of dr, but we're still going from outside in. So our direction for our path length, or our path, is inwards, the electric field is outwards. Thus, the angle in between is 180. And so we get back a negative sign. So negative, these constants come out, q over 4 pi epsilon naught. We have integral b a dr over r squared. Okay. We can evaluate this, another fairly straightforward integral. And so now we have negative 1 over r evaluated from a to b. Okay? And so we got a negative sign, but now it's taken away again. Okay? So it's plus q 4 pi epsilon naught, all these constants stay with it. It does get tedious, but you know, I would not keep this in terms of k, the Coulomb constant. I would always keep it in terms of epsilon naught, right? Then we just evaluate 1 over a minus 1 over b. Okay, we can rewrite this a little bit further, right? A little bit more succinctly. Oops. And finding a common denominator gives us the following. Right? Here I just multiplied the first term here by 1, in other words, b over b, and then the second term by a over a. Okay, so I got this for the voltage. All right, and so that's the expression we plug into the voltage in our capacitance equation, keeping it in terms of Q though. And so Q divided by all that junk, 4 pi epsilon naught, times b minus a over b. Yes, our q's go away, and we're left with 4 pi epsilon naught on the top times ab all over b minus a. And this is the expression for the capacitance for a spherical capacitor. Let's take a look and see if this makes sense. Okay, so the distance b minus a, right? That's effectively the separation distance in between these two plates. So if this separation distance decreased, well, the capacitance overall would increase. And that can happen when the value for A approaches the value of B, or vice versa, right? So if A approached B, well, we'd almost have B minus B, which is 0. And that would be the maximum amount, but that wouldn't really be a capacitor because they'd be at the same spot in space, whatever. As A approached B, the separation distance will decrease, right? It'll be right here. Thus, the capacitance will increase. Another way to look at it is that these values of A and B are radii, right, for the inner and outer conductors. So this 4 pi times radius squared, that's effectively an area, right? So if either of those values, A or B, increased, well, the area increases and the capacity, right, to hold charge increases too. So thus the value of capacitance increases. So our expression here, 4 pi epsilon naught times A times B, all over B minus A, it should match your intuition. Okay, so again, this is how we find the expression for the capacitance for a spherical capacitor.